In this video, I will be introducing the concept of a limit. To start with, we're going to look at this function f of x, and I've provided a picture of the graph of this function. First thing we're going to do is let's go ahead and introduce the notation for a limit. When asked to find a limit, the way it's written is LIM, short for limit. As x approaches a particular value, here I'm going to pick on the particular value 1 of my function f of x. And now let's look at our graph and let's talk about what are we finding when we find the limit as x approaches 1. First, I'm going to start with what we're not finding. So we're not finding the value of my function at x equals 1. If I look at my graph here, I see that there's a hole in my function at x equals 1. So if I were to evaluate the value of my function at x equals 1, we actually find that it's undefined. There's no value of my function at x equals 1. Instead, the question that I'm asking is, as I get really, really close to the x value of 1, what is my function approaching? So essentially, we're going to be looking at x values to the left. So here we're looking at x values getting really, really close to 1 from the left. And we're going to be looking at x values to the right and getting really, really close to the x value of 1. And we're going to be seeing what is the value of my function as I get really close to 1. So we're going to be tracing along our curve. So here, I'll start tracing along my curve to the left of this x value of 1, and I see that as I get closer and closer to 1, the value of my function is approaching 1. Similarly, if I look to the right of 1, I'll trace along my function to the right of 1, and I look at x values getting closer and closer to 1, I see the value of my function is also approaching 1. And that is my limit. We see that the limit as x approaches 1 of my function f of x is equal to 1. And that just means that if I pick x values really, really close to 1, I see that the value of my function is getting really close to 1. Now let's look at an example. Suppose we're looking at the function g of x is equal to x minus 2 divided by x minus 2. And we're asked to find the limit as x approaches 2 of my function g of x. The way we're going to go about this is we are going to graph this particular function and see the behavior of my function as I get really close to 2. The first thing I notice about this function is it seems a bit odd because I have x minus 2 in my numerator and denominator. It's really tempting to just cancel out x minus 2 in my numerator and denominator and say, well, isn't this just equal to 1? And the answer is yes in most cases. So say that my x value is 4. I could look at the value of my function at x equals 4. I would get 4 minus 2 divided by 4 minus 2. I end up with 2 divided by 2. And in fact, yes, the value of my function is equal to 1. However, there is a particular case where this doesn't happen. Let's try, what about if x equals 2? So if I am evaluating my function at x equals 2, I have 2 minus 2 over 2 minus 2. That gives me 0 divided by 0. Okay, so if we have 0 divided by 0, this is undefined. That means that at x equals 2, there's no defined value of my function. So if I were to simplify my function, I have to write this as g of x is equal to 1, and it will be equal to 1 for any finite x value, except I have to say, but not when x equals 2. Now that I've simplified this function, it's easier to graph it because we know how to graph the function g of x equals 1. So let's go ahead and do that. We know that it's going to be the horizontal line at y equals 1, but whenever I get to x equals 2, I know I'm going to have a hole in my graph because my function is not defined there. So we see that this is the graph of my function g of x. Now that we have our graph, we can go back to our initial question, which was, what is the limit as x approaches 2 of my function g of x? And remember, that's asking the question as I get really close to 2 from the left and the right, what is the value of my function approaching? Well, I see that as I trace along my function to the left, it's approaching the value of 1. And same thing as I approach the value of 2 from the right, I see that my function is also approaching the value of 1. So I see that this limit is equal to 1. And we are done. Again, it's really important to notice that the value of my function at a particular x value is not necessarily the value of the limit as I approach that x value. So here we were undefined at x equals 2, but we still have this limit that my function is approaching the value of 1 to the left and to the right of x equals 2. Let's look at one more example. So here let's look at the piecewise function h of x equals, and it's going to be equal to x cubed when x is not equal to 2, and it's going to be equal to 0 when x equals 2. A piecewise function simply means that for different parts of my graph, it's going to be defined by a different rule. So here we see that anywhere that x is not equal to 2, it's just going to be the graph, the cubic graph x cubed, and then when x equals 2, that little other piece of my graph, it's going to be equal to 0. And here the question is asking, what is the limit as x approaches 2 of my function h of x? So first thing that we're going to do again is let's go ahead and graph this function because we want to see what is the behavior of my function as I get really close to x equals 2. I'm just going to graph the first quadrant. And I know that my graph is going to look like x cubed. So everywhere x is not equal to 2, it looks like x cubed, which would look like this in my first quadrant. And then I'm going to go back. So this is, if this is x equals 2, I need to erase because there's a hole here. Oop, that erased a lot. There's going to be a hole in my graph here when x equals 2. It's not following that cubic function. Instead, we see the value of my function at x equals 2 is equal to 0 here. Okay, I'm going to graph another point. So say this is 1. We know that this would be equal to 1. If the value of my function at x equals 2 was x cubed, I know this value here would be 8. Looks like I didn't draw this very well to scale, but we are going to say that this is the cubic function. Okay, so moving on, now that we have our graph, we are going to look at what is the value of my function approaching as I get really close to the x value of 2. So from the left, I trace along my function. I see I'm getting really close to the value 8. Same thing from the right, if I trace along my curve, as I get closer and closer to 2, the value of my function approaches 8. So that tells me that the limit as x approaches 2 of my function is equal to 8. And again, we see that the limit is not necessarily equal to the value of my function at that x value. Here we see that the value of my function at the value of 2 is equal to 0. However, the behavior of my function, as I get really close to 2, the value of my function is approaching 8, not 0. So that tells me that my limit is equal to 8 in this particular case. I do want to show one other way that we can think about this limit without the graph. So one thing that we can do is we can plug in values really close to that x value of 2 in our function. To do that, I'm going to go ahead and set up a table of values. So my x values and the value of my function g of x. The first thing I'm going to do is we always start to the left of that x value of 2. If I start to the left of the x value of 2, I'm looking at numbers smaller than 2. A number smaller than 2 but close to 2, I can choose 1.9. And let's think about what is the value of my function when x equals 1.9. Well, if we go back to the definition of our piecewise function, we see that anywhere x is not equal to 2, the value of my function is x cubed. Well, here x is not equal to 2, so the value of my function must be 1.9 cubed, which if you plug that into your calculator, you get 6.859. Okay? And we're going to want to get closer to 2 from the left. So we're going to choose another value that's less than 2, and we can choose 1.99. That way we're still bigger than 1.9 and we're getting closer and closer to 2 from the left. And again, the value of my function here is 1.99 cubed since that's an x value not equal to 2. And my calculator will give me 7.88 and some long decimal. And again, I'll get one more step closer to 2 if I have 1.999. I'm just going to add another 9 at the end, get a little bit closer to 2. And again, the value of my function is 1.999 cubed. If I plug that into my calculator, I get 7.988. So we see that as we get closer and closer to 2 from the left, I see that the value of my function is getting closer and closer to 8, just like we saw in our graph. We also have to approach 2 from the right. So let's go ahead. If we're approaching from the right, we're looking at x values bigger than 2. I'm going to choose 2.1. I'm starting over on the right on my chart because I know I'm going to be moving to the left. So 2.1 is not equal to 2, so the value of my function here would be 2.1 cubed. My calculator tells me that's 9.261. Okay, and then we're going to take a step closer. To get a step closer, I have 2.01. And again, the value of my function here is 2.01 cubed, which is 8.12 dot dot dot. And then we'll take one more step closer, 2.001. And here the value of my function is 2.001 cubed, which is 8.012. Okay, so we see that as we approach 2 from the right, my values are also getting closer and closer to 8. So here, instead of just looking at the graph, you can plug in numbers that are a little bit smaller than 2 and a little bit bigger than 2 into your function, and you can see that the values are getting closer and closer to 8. So this re-verifies that my limit is equal to 8.